All right, so continuing our lesson from last time, this time the focus truly is on nonlinear regression. Last time we were still mostly looking at linear, actually almost entirely looking at linear models. And in general, there are 6 nonlinear type of models that you should be able to understand and work with and create in the statistics element of this part of this course, all of which using a GDC. Or I should say there's 5 nonlinear, including linear, there's 6. So linear, quadratic, cubic, exponential, power, and a sine function. So these types of functions, we should be familiar with how to create a regression model on our GDC, and all of which we've done actually earlier in the course. So before we get to a bit more of that, just in general, assuming we had data on each type of the following, which type of regression function would be the most appropriate? Starting with the volume of an inflating balloon as a function of the diameter of the balloon. Well, it helps to remember the volume of a sphere, and again, a balloon's not quite a sphere, but the volume of a sphere is 4/3 pi r cubed. This gives us, real sense that this would be a cubic function, which makes sense because volume is a 3-dimensional measurement. So we would use a cubic function to model this data. Even though the balloon likely wouldn't be a perfect sphere, a cubic function would likely make the most sense. Radioactive decay. As soon as we see the word decay, that generally applies to exponential decay, which we've seen before in the course, which means, not surprising, we'd use an exponential function. And finally, the amount of daylight each day over the course of a year. Well, in the summers, there's more daylight. In the winters, there's less daylight. And over the course of year after year, it would oscillate back and forth. That is a sine function. And so we'd use a sine function here for regression. All right. So let's now, for the rest of this, look at this one set of data here, which is showing a comparison between study time and the score on a memory test of 10 students. So first we want to determine, it says that you want to determine how the study time affects their score. So knowing that, what would be the explanatory and responsive variables? And remember again, explanatory are our x variables, or on the x-axis, responsive variables are the y. Dependent, independent as well. So the explanatory variable here, what would go on the x-axis, would be the study time, and because we want to see what effect that has on the score, how it responds. And so in this case, I'll say this would be the study time. And this would be their score. And always that, even if you're not explicitly asked to state that, it's crucially important so that we know when we put our data in, where to put our data. In general, your X column should be the explanatory variables. And if we have them the wrong way around without realizing it, we're actually looking at the inverse of the function. And quite often we can come up with conclusions that are completely inappropriate because we're looking at things the wrong way. All right, so I'll make a scatter plot, and I want to look at the different types of functions. I want to make one of each of these: linear, quadratic, cubic, exponential, power, and sine regression, and then determine which of these would be the most appropriate. And so I will show these graphs, but first I'll also just state here, when we do all these, one thing to pay attention to is your correlation coefficient, the Pearson's R, or that correlation of coefficient of determination. Helps if I can say that properly. So while I will go to Desmos in a moment, I do want to write down that R squared value for each of these, but also not put too much faith into it all on its own. So when you come up with a linear model, which again I will show shortly, that R squared value, I'll write these to 2 decimal places, comes to about 0.89. If you do the same thing for the quadratic, R squared is about 0.96. For a cubic function, R squared is also about 0.96. For an exponential function, why am I writing the word function? R squared would be about 0.86. And for the power function, R squared would be about 0.92. And for the sine function, a TID4 doesn't give an R squared value. However, I know I'm not going to use that one anyways. So my point of writing this down is that I'm not saying these values aren't important, but we want to be careful at jumping to a conclusion just by looking at this. For example, you could go, well, the quadratic or the cubics must be the best, so they have the highest r squared value. But let's also think about what the data represents and how these graphs look. So those will not be actually either the ones I want to use. So let me go to Desmos here. So here's our data. On the x-axis, we have the study time, the y-axis, we have the score. And so a linear regression model looks like this, which makes sense. The more you study, the more you expect, the better score you expect to have on this test. And it's not a bad model. Let's compare it to some others. So a quadratic model, it has a higher r squared value. But if we look at what the model is saying, yes, it comes to the points. Actually, it's much closer to the points than the linear model. But it's really, for most of it, especially for extrapolating, it's a worse model. Now, if we're interpolating, if we're just looking within the data, this could very well be a great model to use. But if we want to extrapolate it all, according to this model, after a while, if you study more, you start to do worse and worse and worse. And considering the nature of the data, that doesn't really make sense. So I don't want to use that. Same thing with the cubic function, which again, comes extremely close to the points. But again, the same problem that as you start to study more than 6 hours, for some reason, that's a tipping point. And after that, things all go downhill with your score. And there's no reason that, if they had some sort of evidence for that to be the case, sure, but we have no evidence for that. Here we have an exponential function, which again models it okay. But this seems to imply that as we study more, not only does the score improve, which we would expect, but improves exponentially, which means, for example, if we studied 8 hours, according to this, we would have a score of 120 out of 60. And that sort of pattern of growth doesn't match what we see here. If we have a power function, this models it quite nicely, and it shows that as we study more, our score goes higher, but it doesn't increase at quite the same rate. If you look at the beginning, a small change in amount of studying makes a big difference to our score, and after a while, a larger change in our amount of studying makes less of a difference. The score still goes up on average, but not as much. This definitely, at least so far, seems to be the most appropriate. It's modeling the points quite well, but it's non-linear. It's not as simple as just a simple linear function, but also it doesn't imply that at some point it starts to go back down. And this will be the one I use, because I don't really need to graph a sine function to know that this idea of it oscillating back and forth is not appropriate for this. And so again, besides just looking at your, let me adjust these scales again. Besides just looking at your correlation coefficient or your r squared value, we also need to think about just the data and what it's telling us. So in this case, it's the power function that I definitely want to work with. And so that's the one, the power function. Has a strong r squared value, and it has a logical connection to the data that we're looking at. So again, those r squared values are important, but we can't be robotic on our thinking and just find the highest one. So now that I'm selecting this one here, what's the significance of that r squared value? We saw this last time. An r squared of about 0.92. This represents that we can say about 92% of the change in a person's score on the test can be accounted for by the change in study time. Now, one thing you want to be careful not to say is don't say, notice I'm saying can be accounted for. Don't say is caused by. Again, we never want to confuse correlation with causation. It's almost certainly some sort of causation there, but what we can just see is statistically the change in one definitely correlates to a change in the other, but don't say it causes it. Because that we can't tell just from looking at a graph, and that's it. So lastly, using our chosen regression model, the power function, I want to extrapolate and predict what would a score be if someone studied 8 hours, which no one went that far. And while we always want to be careful with extrapolating, because we've given a lot of thought into our functions, our prediction here, I think, will be much more valid compared to if we use many of the other functions given. So according to this, we should have a score of roughly 59, depending on, actually, I think the regression model I have here on Desmos is slightly different than the one I have on my TI-84. But roughly it comes to about 59 if you let x equal 8 with our regression model. Y is approximately 59. So approximately a score of 59 is our prediction. We are extrapolating, so we want to be wary of saying this prediction is overly valid. No one actually studied that much in this data. But compared to the others, if I go back and look at for example, my cubic function, which had a very strong r-squared value, according to that, our extrapolating, if you studied 8 hours, we're going to predict a score of 42, which, again, there's no reason for us to think that. So always have to be careful. There's always an element of subjectivity when it comes to, sorry, so let me turn this one off. There we go. There's always an element of subjectivity when it comes to statistics. That doesn't discount its importance. We just want to always acknowledge we can't be fully objective about things. And the first step is to acknowledge the possibilities for variance and be aware that validity there's elements of subjectivity to it.